Imagine stepping outside on a Friday night, just looking up at the sky, and you're watching a star move visibly across the constellation.
Right, like a satellite or something.
Exactly.
Yeah.
But now imagine knowing that the star is actually a 61 billion kilogram rock. And the math says it might come back in exactly 7 years to hit the Atlantic Ocean.
Yeah, that's a terrifying thought.
It really is. And I mean, this isn't some speculative science fiction plot. It is a very real date on the calendar of like every global space agency right now.
Right, and since your calendar currently says May 2026, that means you, listening to this, are less than 3 years away from watching this exact event unfold in real time. We're talking about April 13th, 2029.
Okay, let's unpack this. Today, our mission is to extract the hard science, the astronautical math, and, the planetary defense strategies from this really compelling YouTube script by the channel Dark Matter Files.
Yeah, the video is titled, There's an Asteroid NASA is Watching Right Now. Here's what they're not telling you.
Right, and we're looking specifically at this asteroid named Apophis, which honestly is on a trajectory to pass closer to Earth than the geostationary satellites that run your weather maps and your telecommunications.
It's incredibly close. But to set the baseline immediately, the official stance from both NASA and the European Space Agency is that the 2029 pass is completely safe.
Safe as in, it's definitely not hitting us that day.
Exactly. There's no impact happening on that Friday in April. But the source material we're doing a deep dive on today, it explores the really nuanced physics of what happens next.
Right, because the story doesn't end in 2029.
No, it doesn't. The focus here isn't just on the headline of a near miss. It's a real examination of the mechanics of near-Earth objects and, well, the mathematical uncertainties that follow an event like this.
Yeah, and to really understand why that 2029 flyby is so critical, we have to look back at the sheer panic of its initial discovery. Because the relief scientists feel today, it was earned through a pretty grueling process of elimination.
Oh, absolutely. The timeline starts back in June 2004. You had these astronomers, Roy Tucker, David Tholen, and Fabrizio Bernardi. They were working at the Kitt Peak Observatory out in Arizona when they first spotted the object.
And the scale of Apophis is just... it's difficult to conceptualize. I mean, it's 370 meters wide.
Right, which is roughly 3.5 football fields laid end to end.
Yeah, but the mass is the truly staggering figure here.
Yeah.
61 billion kilograms.
It's a number so big it almost loses its meaning, right?
Totally.
Yeah.
But the source script puts that mass into a really sharp perspective. It points out that it weighs more than every single aircraft ever built by humanity combined.
Wow. Yeah, that really paints a picture.
Right, and it is traveling at 30 kilometers per second, which is about 30 times faster than a standard rifle bullet.
So you take an object with that massive weight, moving at that insane velocity, and when they ran the initial trajectory calculations, it resulted in a massive alarm bell for the scientific community.
Because the initial data showed a 2.7% probability of impact in 2029, right?
Exactly. And in the world of planetary defense, a 2.7% chance is monumental. It is the highest impact probability ever recorded for an object of that size.
The source actually compares it to playing Russian roulette with a 37-chamber revolver.
That's a great analogy. You've got 36 empty chambers, but the one loaded chamber is pointed directly at Earth.
Yeah, but the reaction to that discovery is where I want to push back a bit on our typical expectations of transparency.
How do you mean?
Well, the source notes that the scientific community went completely quiet for 48 hours. Governments were privately briefed, but the public was kept totally in the dark.
Right. They locked down the information.
Yeah, and if astronomers knew an object that fast and that heavy had a 2.7% chance of ending millions of lives, my instinct is that you issue a global warning immediately. So governments can, prepare. Going dark for 2 days feels like a dangerous withholding of critical information.
I get that. It feels counterintuitive. But the withholding of that information was actually a necessary application of scientific rigor over public panic.
You think so?
Definitely. You have to consider the immediate real-world consequences of announcing a 2.7% probability of a civilization-altering impact before you've rigorously tested the math.
Oh, I see. Like, the panic will be worse than the rock.
Basically. You'd trigger instant global market crashes, civil unrest, and preemptive mass migrations away from coastal areas. I mean, the devastation of the announcement itself would be very tangible.
Right, people would just lose their minds immediately.
Exactly. So those 48 hours of silence acted as a firewall. Scientists used that time to scour astronomical archives, looking for older, faint images of the sky to refine the orbital arc.
They need more data points.
Right, they had to be absolutely certain of the parameters before triggering a worldwide response.
Which, I mean, that level of high-stakes verification really explains why the asteroid was eventually named Apophis.
Yeah, the Egyptian god of chaos.
Right, the god of chaos and darkness, the serpent that constantly tries to swallow the sun. They weren't just picking a dramatic name out of a hat, you know. They were looking at the raw math of a potential doomsday.
It's a very fitting name, and thankfully, the subsequent data allowed them to rule out the 2029 impact entirely.
A huge sigh of relief.
Yes, but resolving that immediate threat just opened up a secondary, far more complex physics problem.
Right, the keyhole.
Exactly. Because it's passing so incredibly close to Earth, Apophis subjects itself to our planet's immense gravitational pull, which literally alters its orbit around the sun.
Let's break down the mechanics of that close pass, because the precision involved here it's just hard to wrap your head around. In 2029, Apophis passes about 31,000 kilometers above the surface.
Which puts it inside the orbit of our high-altitude satellites.
Yes, threading the needle. And as it rips through that space, Earth's gravity will bend its path, and scattered across that approach corridor are these regions of space called gravitational keyholes.
Right. And a gravitational keyhole is this microscopic, mathematically defined region in space.
Microscopic in cosmic terms, anyway.
Yes. And if Apophis passes through one of these keyholes, Earth's gravity will alter its trajectory by the exact, precise degree needed to put it on a guaranteed collision course with Earth when it orbits back around.
In April 2036.
Exactly. Think of it like a trick shot in a game of pool.
Okay, I like that.
The keyhole is the exact millimeter on the side of the 8-ball you have to hit. Earth's gravity acts as the pool cue, applying the exact force and angle required to bank the asteroid across the solar system and sink it perfectly into the corner pocket 7 years later.
That's a terrifying visual. But the scale of that pool trick shot is what absolutely baffles me.
Yeah.
I mean, Apophis is 370 meters wide, right?
Right.
And the source points out that the primary keyhole for the 2036 impact is only 800 meters wide.
Yep.
Wait, that margin of error is basically the size of the asteroid itself? How can we possibly calculate an 800-meter target from millions of miles away? It seems physically impossible.
What's fascinating here is how radar telemetry allows us to measure velocity in deep space.
Okay, how does that work?
Well, planetary scientists don't just look through optical telescopes. They bounce highly focused radio waves off the asteroid using massive facilities like the Goldstone Observatory.
Oh, like echolocation.
Basically, yeah. And previously, they used the Arecibo Observatory before it collapsed. By measuring the Doppler shift of the radio echo that bounces back, they can calculate the asteroid's speed down to fractions of a millimeter per second.
Fractions of a millimeter? That's insane.
It's incredible tech. And that precision is what allowed them to significantly reduce the probability of Apophis hitting that 800-meter keyhole.
Right. But, and this is a big but, the gap between significantly reduced probability and absolute zero risk is a very uncomfortable gray area.
Very uncomfortable. It totally changes the psychological reality of the event.
Because we'll know.
Exactly. If the universe rolls the dice and Apophis somehow threads that 800-meter needle in 2029, humanity will suddenly have exactly 7 years of knowing with absolute mathematical certainty that a catastrophic impact is locked in for 2036.
So if the math locks in that 2036 impact, what does that mathematical certainty actually look like? Like when 61 billion kilograms of rock hits the atmosphere?
Well, the kinetic energy models in the source material project a release of approximately 1,200 megatons of TNT.
1,200 megatons?
Yeah. To contextualize that, it is roughly 80,000 times more powerful than the atomic bomb dropped on Hiroshima.
Oh my God, 80,000.
And when scientists model an impact of that magnitude, they categorize it by the impact medium. So either an ocean strike or a land strike.
Right. And the ocean strike scenario the source focuses on is the North Atlantic.
Yes.
If a 370-meter rock hits deep water at 30 kilometers per second, it transfers all that kinetic energy into an incompressible fluid. The water has to go somewhere.
And it goes everywhere, fast.
Right. The initial water displacement generates a mega tsunami. At the point of impact, you have this temporary crater in the ocean itself, bordered by waves 500 to 800 meters high.
It's almost unimaginable. And those waves propagate outward through the deep ocean at basically jetliner speeds.
Wow.
But the real devastation occurs when that kinetic energy reaches the shallower waters of the continental shelf.
Because it hits the bottom.
Exactly. The friction of the rising seafloor forces all that energy upward in a process called shoaling.
Right, so the wave stands up.
Yes. By the time those waves reach the eastern seaboard of the United States, so New York, Boston, Washington, D.C., Miami, they arrive as walls of water 30 to 50 meters high. 30
to 50 meters. That is a 15-story building of seawater just hitting the coast.
Yeah.
Lower Manhattan floods in a matter of minutes. The entire 245-mile subway system becomes a subterranean river instantly.
And it's important to remember, the physics don't care about borders. The waves travel outward in all directions.
Right, so Europe and Africa get hit too.
Exactly. Cities on the other side of the Atlantic, like London, Lisbon, and Lagos, face the exact same catastrophic inundation.
It's truly apocalyptic. And then there's the alternative scenario, right? The continental land strike.
Right, which trades a mega tsunami for atmospheric devastation.
What does that look like?
Well, the immediate blast radius, which is an area of total vaporization and complete structural collapse, is modeled at roughly 150 kilometers across.
Just gone.
Just gone. But surprisingly, the localized blast is not the primary mechanism of mass casualties.
Right, the primary mechanism is what happens to the pulverized ground. The impact forces thousands of tons of vaporized rock and debris up into the stratosphere.
And because the stratosphere is above our weather layer, there's no rain up there to wash that dust back down.
So it just stays there?
Yeah. It spreads across the globe, creating this high albedo barrier that reflects solar radiation back into space, which triggers an impact winter that could last 3 to 5 years.
So what does this all mean? Because, I mean, the asteroid that wiped out the non-avian dinosaurs 66 million years ago, that was roughly 10 kilometers wide.
Right, a massive object.
And the Apophis is only 370 meters wide. It seems counterintuitive to me that an object comparatively that small could still collapse civilization. Are our infrastructures really that fragile?
Well, to be clear, Apophis is absolutely not a planet-killer rock in the vein of the dinosaur extinction.
Okay, that's somewhat comforting.
Yeah, a 370-meter impactor will not boil the oceans or cause a sudden mass extinction of all life.
Right.
But the vulnerability lies entirely in the fragility of our human ecosystem. A 3 to 5 year impact winter means global agriculture fails almost immediately.
Because nothing can grow without sunlight.
Exactly. And without a harvest, the interconnected global supply chains snap. The models predict a minimum of 1 billion casualties, not from the initial explosion, but from the cascading domino effect.
Sudden famine, critical infrastructure collapse.
Rampant disease, and immediate violent geopolitical conflict over whatever dwindling resources are left.
Wow, that fragile domino effect completely recontextualizes how the world will experience the 2029 flyby. The visual reality of that night is going to be incredibly surreal.
Oh, without a doubt.
Like April 13, 2029 is a Friday. At 9:46 p.m. Eastern Time, Apophis reaches its closest approach.
And because of its proximity and the highly reflective nature of its surface materials, Apophis will reach a visual magnitude of 3.1.
What does that mean for the average person looking up?
Well, in the astronomical magnitude scale, which is logarithmic, lower numbers mean a brighter object. For comparison, Sirius, the brightest star in the night sky, is at roughly negative 1.4.
Okay.
A magnitude of 3.1 means Apophis will be as bright as the stars making up the Big Dipper.
Meaning you won't even need a telescope. You will literally just look up and see a point of light moving across the sky.
Right, in real time.
The source notes that for an 18-minute window, approximately 2 billion people across a massive swath of the globe-like, stretching through Cairo, Mumbai, Moscow, Nairobi, and Istanbul, they'll all be able to see it simultaneously.
And during those 18 minutes, the observation won't be limited to just the official space agencies. You will have a massive influx of citizen scientists.
Right, guys in their backyards.
Exactly. People with advanced backyard telescopes or even standard smartphones will be tracking its trajectory and feeding that positional data into open source systems in real time.
It's crowdsourcing planetary defense.
Yeah. And within roughly 6 hours of the closest approach, the scientific community will have the telemetry needed to know if it hit that 800-meter keyhole.
Here's where it gets really interesting. Imagine 2 billion people holding their breath for a 6-hour waiting period while raw data floods the internet.
It's a recipe for chaos.
Right. You are guaranteeing to see massive global panic. Amateur data will be misinterpreted on social media, with people running their own flawed math and declaring that the keyhole was hit before official agencies can even verify the complex Doppler measurement.
If we connect this to the bigger picture, the potential for misinformation during those 6 hours is profound.
It'll be trending everywhere.
But the event itself is unprecedented. I mean, no single astronomical phenomenon in recorded human history, no solar eclipse, comet, or meteor shower has been watched by 2 billion people simultaneously.
That's a wild statistic.
It really is. It represents the staggering moment of global unity, but a unity that's anchored by a very deep, shared existential dread.
Yeah, staring up at a rock that might kill us. But if that 6-hour wait ends with the worst possible news, like if the math confirms it threaded the keyhole and is coming back in 2036, humanity's not going to just sit on its hands and wait for the end.
No, absolutely not. We actually have an active, tested planetary defense playbook.
Right, and that playbook made the jump from theoretical physics to documented fact very recently, in September 2022.
Yes, when NASA executed the double asteroid redirection test, the DART mission.
Which was basically playing cosmic billiards.
Essentially, yeah. The objective was to deliberately crash a spacecraft into an asteroid named Dimorphos, serving as a kinetic impactor.
And the goal was to change the asteroid's orbital period by just, 73 seconds?
That was the baseline for success, yes.
But instead, the kinetic transfer was so effective that they shortened the orbit by 32 minutes.
They smashed expectations. They proved that moving a celestial body is purely a matter of applied physics.
So deflecting a threat like Apophis doesn't require detonating a nuclear weapon to blow it to pieces, like in the movies.
No, definitely not. That would just create a shotgun blast of radioactive rock heading toward Earth.
Which sounds way worse.
It is. You simply need to give it a kinetic nudge of about 1 kilometer to alter its trajectory enough to miss the Earth. But the physics of that nudge are entirely dependent on lead time. Well, if you apply the kinetic impact 10 years before the collision date, you only need to change the asteroid's velocity by centimeters per second. That tiny change compounds over billions of miles.
Just a little tap early on.
Right. But if you wait until you are only 1 year out, you need to change its velocity by meters per second, which requires exponentially more energy than we can currently launch.
And that timeline constraint is exactly what worries me. I mean, if we find out in 2029 that the keyhole is hit, we have a firm 7-year deadline.
Yep, 2036.
7 years sounds like a long time, but consider the logistics. You have to achieve political consensus across multiple nations, secure billions in funding, engineer and build the spacecraft hardware from scratch, successfully launch it, and account for the travel time to actually intercept the asteroid in deep space.
It's a massive order.
Right. Global bureaucracy moves incredibly slowly. Designing and launching a bespoke, flawless space mission in 7 years seems nearly impossible. Isn't that terrifyingly fast?
I agree completely. It raises a really important question about institutional agility. And it is the exact reason space agencies aren't waiting until 2029 to prepare.
Oh, they're already on it.
Oh, yeah. NASA's Center for Near-Earth Object Studies at the Jet Propulsion Lab, alongside the European Space Agency's Space Safety Program, they maintain independent 24-hour tracking operations.
So they're watching it constantly.
Exactly. And there are already dedicated hardware missions planned for the 2029 flyby. The ESA is launching the Hera mission, and there are planned observational flybys from Japan's JXA, China's CNSA, and NASA.
Getting ahead of the curve.
Right, they're gathering the granular data now so that the engineering parameters are already known if a deflection mission is ever actually required.
You know, it is worth mentioning that in 2021, NASA actually removed Apophis from its Century Risk Table. Based on their current models, they ruled out the 2036 impact.
The operative word there being current models?
Right.
Because the mathematics of the solar system are never permanently settled. It is what physicists call an n-body problem.
Meaning there are too many moving parts.
Exactly. Every time Apophis orbits, it is subjected to the gravitational tugs of Jupiter and Mars. And more importantly, it's subjected to the microscopic pressure of sunlight itself.
Right. Sunlight can push a rock.
Yes. As the asteroid rotates, it absorbs solar radiation and radiates it back out as heat, which acts like a tiny, continuous thruster pushing against the rock.
That's crazy.
Over years, that subtle pressure constantly alters the trajectory. And Apophis is just one object. There are roughly 1,400 other potentially hazardous asteroids currently being tracked.
So, for you listening to this, the ultimate takeaway isn't panic. It is really the realization of our own technological evolution.
We've come a long way.
We really have. The reason we are not doomed to be blindsided like the dinosaurs is that we built a 20-year margin of warning. Between the 2004 discovery and the 2029 flyby, humanity has utilized radar dishes to bounce signals 10 million miles into the dark just to map a rock we could barely even see.
It's awe-inspiring.
Yeah. We engineered a spacecraft, flew it into the void, and literally moved a mountain in space. It is undoubtedly one of the most astonishing things our species has ever achieved.
It's a remarkable testament to human ingenuity, but the lingering thought to mull over as we wrap up this deep dive is the realization that planetary safety is not a permanent locked-in state.
Right, it's not a guarantee.
No, because the universe is not a static backdrop. It is a highly dynamic, ever-shifting clockwork. Distant planets exert gravity, and the microscopic pressure of sunlight constantly pushes against the 61 billion kilogram rock.
So the math is always changing.
Always. Our mathematical safety is highly temporary. It is incredibly fragile. The slight variation of solar radiation over millions of miles could eventually be the difference between a near miss and a global catastrophe.
That shifting math means the diagnostic landscape is never fully at rest. It demands our eternal vigilance. Keep looking up.